good day. I welcome you once again to our class, the training which has been organized by Noble Mind Spectroscopy, or Team Spectra as you may call them, and some other resource persons have discussed mass spectroscopy, and some have talked about the Fourier transform infrared spectroscopy. And in my previous classes I have discussed UV visible spectroscopy, and most recent, the nuclear magnetic resonance spectroscopy, which we know as NMR. So where I discussed the proton NMR and the introduction to NMR. In today's class, I shall be discussing carbon-13 NMR. If you look at the figure as been presented on the slide, you could see the relative abundance of carbon isotopes, which display carbon-12 as 98.9% abundance, carbon-13 as 1.1%, and infinitesimal amount of carbon-14, radioactive carbon-14. So we are concerned about carbon-13, which has a spin angular momentum of plus or minus half. And if you want to say why not carbon-12, carbon-12 has a spin angular momentum of 0, so that could not be observed in NMR. So the number and type of carbon atom which is in a particular compound may be determined using carbon-13 NMR. Let's also talk about the magnetic moment of carbon-13, which is about 1/4 of the magnetic moment of proton. Proton has about 2.7927, and if you check the values for carbon-13, you discover that it's about 1/4 of that of proton. So when considering the signal of carbon-13, it is relatively weaker compared to that of proton NMR in the spectrum. We have discussed so many things in proton NMR, and we will still be mentioning them as they are applicable to carbon-13 as well. We discussed what environments were in proton NMR, so you can refer back to our previous classes to understand that. So let's look at different structures of molecules, or what you may call them, and see the number of environments they have. If you look at the first structure, we say it has 2 environments. If you group them based on the nature of surrounding atoms, you check it very well, you discover that those ones that are grouped as A, environment A, they are a CH3, which is a CH3 bonded to CH2, and the other side CH3 bonded to CH2, so they have similar environments. If you look at those that are called B, CH2 bonded to CH3 then to CH2. If you consider the other CH2 as well, is similar, so we group them as having 2 environments. So if you look down under that, you have a pentane molecule, and based on the judgment we used for the previous molecule, we discover that pentane has 3 carbon environments, and so on and so forth. let's see the one that is very interesting here. Benzene ring. Okay, all carbon in the benzene ring which is not substituted, okay, unsubstituted benzene ring, have the same environment. But the amazing thing is that immediately you introduce a substituent, it changes the nature or how the environment appears. What you just do is, if you want to know the environment, try and look at the carbon and look at which atom, the carbon they are bonded to. You have a CH3, okay, it's being bonded by the left to CH2, it's being bonded by the right to CH2, so to say. You consider each of the carbon atom one after the other, and you group those that have similar environment, or that are bonded to similar atoms. You group them to having same environment. So you may look at the different example of structure as presented on the slide. You will actually understand what I'm talking about. Let's talk about signals in carbon 13. Unlike proton NMR signal, which are being splitted due to what? Due to coupling by neighboring environmental or neighboring protons in the environment. Carbon 13 appear as a single peak. So the peak of proton in the NMR spectrum, the peaks you have from a particular signal is due to coupling. Okay, in carbon 13 you observe only one signal, and that is due to what is called decoupling. Okay, proton, we'll talk about coupling. In carbon 13 we'll talk about decoupling. So intensity of a peak, of a particular peak, it indicates the number of carbon atoms that are in the same environment. Let's just briefly talk about types of carbon atom and their multiplicity. If you have a CH3 carbon, CH3, we call it methyl carbon, and multiplicity is a quartet. CH2 methylene carbon triplet, CH methane carbon doublet, and C is a quaternary carbon that has a singlet multiplicity. So we go straight to the chemical shift in carbon 13. We have defined that so well in proton NMR, and a range of values has been given from the reference material, the reference compound TMS, tetramethylsaline, which has a shift of 0, chemical shift of 0. So every other compound were being discussed as taking shift away from the reference material. So, and the approximate value of this shift were given on the table below. So you may look at the table below and use it to understand the figure where the shift were presented. If you see, look at the shift around 190, 196 or thereabout to around 220. Okay, that could be due to the presence of functional groups, which you'll be talking about. Maybe the ketone functional group. Yes, talk about ketone functional group or aldehyde functional group. The one between 165 to 185 may be due to carboxylic acid or ester. You could see from 155 to 185 where you have the amide, the nitrile from 110 to 140, and so on. So you could look at that and understand. All these will be useful during the process of interpretation of NMR spectra. Let's discuss briefly the factors affecting carbon 13 chemical shift. Okay, the first factor here is alpha, beta, and gamma substituent effect, and we say the presence of this alpha, beta, and position it results into the shift of absorption towards downfield. You say increase in chemical shift. We have discussed that in previous slide, previous presentation, where we talk about proton NMR. So I'm referring to that. So that will help. Read more about or watch the presentation about proton NMR. So all the references will be clear to you. So when there is a substituent, or you have presence of substituent at the gamma position, it results into shift of absorption band towards off-field shift. You have the decrease in chemical shift, and there is a formula for calculating what happens to a chemical shift at the overall. You have this formula, 2.5 plus 9.5 number of alpha carbon plus 9.4 number of beta carbon minus 2.5 number of gamma carbon plus 0.3 number of theta carbon. As a chemistry student, I hope you should be able to understand what alpha carbon, beta carbon. So if you are considering a particular carbon, okay, place your hand or place your cursor on that carbon. Okay, that's carbon number 1. The carbon next to it, okay, which you could call number 2, okay, could be referred to as alpha carbon. The one that you could call number 3 becomes beta. The one that you could call number 4 becomes gamma, and the likes and the likes. So we have another factor that may contribute to chemical shift, maybe alpha, beta, and gamma substituent effect, which is electronegativity of substituent, the type of substituent that are present. That has been discussed in proton NMR, so we may refer to that. The second factor is hybridization effect. Just from where we define the type of carbon atoms, where we have the methyl, the methylene, the quaternary, and the likes. So you could see that hybridization of a CH3 is different from that of CH2, is different from that of CH. Okay, so the particular hybridization that a particular carbon is participating or that is exhibiting would affect the chemical shift of such carbon. Go back to where we have the carbon-13 chemical shift. You could see that for those that are saturated alkanes, generally you could see where their chemical shift was found, and for the alkenes you see their chemical shift, and those for the unsaturated alkynes you see where their chemical shift was. So you could go back and observe what I've just discussed. The third factor here is ring effect. Okay, let's talk about 3-member ring. For example, we have different 3-member ring here. So you have cyclopropene, and look at epoxide, look at aziridines, and so on, like that. You could see carbon number 2 in propane. Okay, in propane, carbon number 2 has has a 16 as a chemical shift. But look at cyclopropane. Okay, so the ring has affected the chemical shift, and it affected it shift the chemical shift of that carbon number 2 to a lower chemical shift. You call it upshift. So the C2 for all the compounds or molecules being displayed on the slide is being affected by the nature or the type of ring they are participating, where they are participating. So you don't assume that all rings, number 2 in all 3-member ring is always the same, or carbon number 1 is always, depending on the environment where they are participating. Okay, that will also affect their chemical shift. here, number 4, we talk about conjugation to carbonyl group. Okay, influence of conjugation. Okay, either aromatic or aliphatic double bonds with carbonyl carbon. Okay, decreases the chemical shift. We call it upfield shift. Okay, and that depends on type of carbonyl compound, which is I hope you know there are so many compounds may have carbonyl compounds. You have aldehydes, you have ketones, you have carbonyl functional group in carboxylic acid as well. You may have that in halide, you have it in esters, and so on. So depending on the type of carbonyl carbon that you are having, so there may be a decrease in the chemical shift due to conjugation to carbonyl group between 6 to 10 ppm. Okay, let's present the structure below, and you see we have the structure butan-2-one. Okay, if you check the chemical shift of butan-2-one is around 206 part per million ppm. Then when the carbonyl carbon is now involved in conjugation, okay, as is involved in conjugation as in structure 2. Okay, the observation of a chemical shift was reduced to 197. Okay, and if it by the time it involved in acetophenone or acetophenone, you could see that the chemical shift has reduced to 195. So those conjugation of a particular carbon to a carbonyl group, okay, could also have influence on the type of on the chemical shift of the particular carbon. Hydrogen effect, that's number 5. So there may be intramolecular hydrogen bonding, which may affect the chemical shift towards higher value downfield. You should, or you may check in the proton NMR. We have something shielding effect, okay, and de-shielding. Okay, so you will truly understand the influence of electronegative atoms on a particular compound. So they may have a strong influence on the values of chemical shift. As we have said in the beginning of the training, there are much to discuss, but we have just limited time. And I must appreciate the team Spectra or Noble Minds group for being able to cover much, even within the limited time that was available to them. I want to inform you that the training, as is being suspended or coming to an end, we still have a future studies that may want to understand fully what NMR is. So, and then in future studies you may be reading about 1D and 2D NMR, part of which we have discussed. We have discussed correlation, J constant, environment, important NMR, all of those ones. But 2D NMR, you shall be talking about. Okay, you may read about. You may read about correlation spectroscopy, COSY, distortionless, enhancement of polarization, transfer, depth. We have depth 45, depth 90, and 145, and there are experiments on their own. So we have HSQC, we have HMBC. All these are interesting experiments, and in fact, that is when you can truly understand the interpretation of NMR signal. So that's important for you. It's important for you to do further studies in order to actually understand fully what NMR is and to be able to use the spectroscopic method in structural elucidation. At this point, I must thank the Noble Minds team for giving me the opportunity to be one of the facilitators who discussed the UV visible spectroscopy as well as the NMR. What we have been able to discuss is a factor of time, but I believe that even within the limited time that has been available to us, we have been able to do justice to the UV visible spectroscopy and NMR. So the aspect of NMR that is left, as I've placed on previous slide, is that which you may read about the further studies. So some 2D NMR experiment. So these are a few resources or resource materials that I consulted. I hope to see you again. I hope to come your way again as a resource person. I hope to do justice to further topics ahead. I hope to see you with much of knowledge as regards spectroscopy in future. Once again, I am Samuel Adewale Adeboyega from Department of Pure and Applied Chemistry, Ladoke Akintola University of Technology, Ogbomoso. I thank you for your cooperation.